So as our speaker for the first sessions are almost done, almost ready. So probably we are going to go to our first session that I'm going to moderate. So just also for general information, I'm going to tell you how will be the mechanics of the sessions. So we are going to have 3 speakers in each session, and each speaker will have 30 minutes. They will give us a 30-minute presentation. The presentation will be back to back. So after the 3 presentations, we are going to have a 30 minutes discussion panel where attendees or the speakers also will answer questions, and attendees can ask questions via the way that Elizabeth already explained. So first, the 3 presentations back to back, 30 minutes each. And then after the 3 presentations, the discussion panel for 30 minutes. So this is the way how we are going to operate that. And then after the discussion panel, we are going to have a 15 minutes break. All right. So our first speaker for this session is Professor Susan Carter with the University of South Carolina. And the title of the presentations is Disaster Inequality and Equitable Risk Reduction. Yeah, for the sake of time, we are not going to read the bios. I think the bios are already available in the website of the event. So for more information about them, you can go into the website. Okay? So it's for me a great pleasure, a great honor and privilege to introduce to all of you Professor Susan Carter.
Thank you very much. Can everybody hear and see the screen? Let me go ahead with the presentation and then I'll get back in.
We can hear you and we can see your presentation just fine. So hopefully we can get out the Q&A. No worries.
All right. Perfect. All right. What I want to start with is a little bit of background about some of these global changes that have taken place, which influence risk, disaster risk in particular. We see that there's been major alteration of natural systems from local to global. We've seen changes in demographics. We've seen changes in public trust throughout, not only locally, but to globally. This has influenced how we've come to understand disasters in our daily lives. We used to think of it as being a very linear association, but increasingly, particularly at the global level, we're recognizing that disaster risk is reflecting of nonlinear change. It has a lot of complex dynamic systems with interdependencies, differences in scale, and place-based contexts really are influencing the production, but also the impact of these disasters. We have new tools and methods that allow us to look at data in different ways and to collect data in more sophisticated ways, which helps us to understand some of these complexities that we're beginning to see. And more significantly, we see that there are large-scale differences in disaster governance. And this change in disaster governance is occurring locally to globally and is obviously shaped by the social and economic forces at play, along with demographic changes. What this means is that there are increasing disparities in disaster governance. There are increasing difficulties in scales and how we manage emergencies. And all too often, our emergency management has become more reactive and fragmented over time. What this background leads to are actually changes in hazards and hazards management. And one of the first changes or considerations is that we have actually moved from extreme and non-extreme events. that our alteration of the natural systems has resulted in extreme events are now becoming annual events or seasonal events, or oftentimes everyday occurrences. We see wildfires that used to be occasional are now frequent. We see that population growth and demographics and distributions has put more people at risk. And therefore, these antecedent conditions are increasing the impacts of this risk. And we see that there are increasingly continuous impacts that we may be experiencing, we being collectively society, may be experiencing catastrophic damage from non-extreme events, but we're also seeing that there's inefficient recovery time before the next event occurs. How we go about defining extreme is important, particularly in how we measure it. And from a natural science perspective, we may be defining extremes based on the intensity or frequency or magnitude of an event. We're looking at the tails of the distribution of a normal curve, for example. But if we turn that around and we define extremes based on human impact, that is the example on the screen is the $1 billion weather and climate disasters. What we're seeing is an increase in the extremes, an increase in the number of $1 billion disaster events. So now we have to perhaps think of $10 billion as an extreme. So our consideration of what does extreme mean has been changing. At the same time, we are beginning to see more and more compound or cascading events. And this results in a larger potential for disruption at regional to global economies, oftentimes can result in humanitarian crises because of the interdependencies that we see between the global systems and technology, for example. We're also seeing increasing exposure through vulnerability and societal risk production. And we see this in this example of the cold wave that hit Texas that resulted in power loss, that resulted in deaths and hypothermia of a large number of vulnerable populations. And we're beginning to see these unintended consequences from everyday events, such as rain and heat and cold. What these cascades have done is they have, in many ways, reduced the capacity of many places to adequately respond to, recover from disasters. And some of this social cascades are reflective of this reduced capacity because of the frequency of these events occurring. The Puerto Rico case is a great one, where there were 3 major large hurricanes that affected the island in 2017. Or we see a place in Central America which had 2 Category 4 storms affect a similar place within a 2-week period. This repetitive nature of these events creates a multiplier effect and ultimately reduces the capacity of these communities to recover. Ultimately, these cascades are becoming a new normal. We see rapid succession of events that are hitting the same region over and over again. You see it in terms of the Gulf and the Atlantic coasts with hurricanes. You see it in the West with wildfires. The cascades then are affecting the aging infrastructure. You put on that social unrest, which is increasing, and of course, COVID-19, the pandemic, all of which has influenced us now as being in this new normal of cascading events. If you layer on top of that the persistence of these disaster inequalities, which are a result of the racial and economic divides in society that are in and of themselves based on the historical processes and patterns and structural outcomes, we begin to see a widening of wealth inequality, of gender inequality, of access to technology inequality. And this means that within generations, this inequality is persisting, and it's persisting in significant places where the disaster losses and impacts are increasing, and they're increasing to such a degree that they're really accelerating faster than the capacity of places to cope with them. And that means they are increasing the inequalities and increasing the vulnerability. So we have a situation where we have major inequalities from local to global scales that we need to address. And the way in which we address them is to reduce the inequity in society. And we have to recognize that just because we say there's inequality or inequity doesn't necessarily mean that there's proof, that there's empirical proof. And the idea is we need an apolitical way of helping those most in need so we can achieve equity in disaster recovery, which is the ultimate goal. So to sum, for at least this section, we see that there is the changing nature of hazards and their management, that these large singular extreme events are consequential where they occur. But we may see that they have cascading impacts that go from the local to the global. We may also see that there are less extreme events that actually may be more impactful in the longer term in particular places as we transition to this new normal of events. Cascading disasters, I think, are now the norm, and we still continue to see major inequalities in disaster risk, and this inequality is actually accelerating. So how do we address this? How do we address these concepts of extreme events, cascading disasters, and inequality? And I have 4 suggestions. The first is to understand the context within which this is all occurring, because the contexts differ. To provide the evidentiary basis for pre-existing conditions in places to their exposure, their vulnerabilities, their capacities to recover. We need to look at these differential abilities of communities or individuals to respond and recover. And we need to demonstrate and actually engage with these principles of equity and fairness. So how do we understand the context? Well, what we can look at are patterns, and we can look at county loss patterns, for example, in the United States. And we can see that the per capita losses of climate-sensitive hazards is increasing over time. We can see that there is a spatial distribution to the average annual property loss, the figure on the left. And we can see that those losses related to climate-sensitive hazards are concentrated in a number of areas: Southern California, the Gulf Coast states, portions of the South Atlantic coast, and then in the Northeast. But we can look at that as well as per capita loss. And there you see that the picture changes a little bit, where we see per capita losses are actually higher in the central part of the U.S., in particular the Mississippi Valley regions. We can also look at the context, which is that there is diversity in the risk, that the location relative to one's surroundings also contribute to your disaster risk makeup. The remoteness of the location, the level of development. Certainly we know that development encroaching on wildlands increases wildfire risk. We know that climate change of the natural system influences the health and structure of economies. And we know that the transformation from extractive economies to service economies provides less stability in the tax base in many of these places. And that lack of stability in the tax base influences the capacity and the governance structures within communities. So understanding the context of a particular place is one way of beginning to move toward enhancing risk resilience. The second one is knowing your risk and exposure and your vulnerability. And here, this is the use of natural hazard information, which many of you are familiar with in terms of the earthquake context, and looking at the frequency of occurrence of that particular risk source, and creating a metric that allows you to look at the expected average annual loss. The picture here looks at wildfires, starting with the burn probability of wildfires, and then added to that the number of events per year, a frequency indicator, and then looking at losses in terms of expected annual losses. And you can see that California clearly is high on all of those measures, but we do see that there is wildfire risk in other parts of the country, most noticeably in Florida for places east of the Mississippi River. Another way of looking at this risk and exposure is to think about, well, what is the relative loss? In other words, what is the ratio of the property loss to an economic measure like county GDP? This provides us with an indicator, an empirically based indicator of the capacity of a community to actually absorb loss. $1 million loss in a wealthy area like Los Angeles County is far less impactful than $1 million loss in a rural South Carolina county, for example. And so you can see on the top map of the US, the total property loss from 1980 to the present, and you can see concentrations in the darker hues, the reds. But when you look at the relative impact, you see that that picture changes a little bit. And these property losses actually are more impactful in other areas, particularly, again, in the Great Plains states. We can look at this a little bit differently as well by looking at the impacts from social vulnerability. That is, if we look at these losses or the impacts, are they disproportionately affecting those most vulnerable places. This is a reconstruction using the Social Vulnerability Index, showing those places, those counties in particular, that have higher levels of social vulnerability versus those in the blue, which have lower levels of social vulnerability. You can take this approach and look at, again, using the wildfire example, look at the average wildfire risk, the likelihood of the burn, and you can put those two together with the social vulnerability index in a empirically based bivariate map to show where the greatest impact is. And the greatest impact is in those dark maroon areas, not necessarily in Southern California, but more in Northern California, as an example. A third way that we need to move is to assess our different capacities and abilities. We recognize that all places are unique and that the location of the place, its site, and its geographic context certainly influences the vulnerability and the coping capacity. The site in particular represents those physical attributes of particular places. And again, we can go back to the previous example of the wildfire risk, the burn probability. We can add the social vulnerability there, but we can now add a measure of the likelihood versus the capacity of those areas to absorb those losses, or a resilience measure, an empirically based resilience measure. So we're starting to move and assess the differential capacity of places in addition to the impacts, in addition to the basic parameters of risk and exposure. And this leads to the fourth point, which is the need to address fairness in recovery. And here we have some very nice empirically based examples where you can use this information on impacts and vulnerability to highlight those areas that have residents that are most in need. And in this particular map from South Carolina, from the 2015 floods, what we see are those dark maroon areas are those places where they had the most vulnerable residents and they had the most impact based on FEMA verified flood losses. This was done in response to our governor, who wanted to avoid the utilization of scarce recovery resources for everybody, and she wanted to target those areas that were most in need and most vulnerable. And she wanted an apolitical way of doing that. And so they employed the Social Vulnerability Index to achieve that recovery. And they targeted recovery resources, state recovery resources and federal recovery resources from HUD into those areas that were most affected based on the FEMA verified losses, but also most socially vulnerable. In other words, those areas that were the dark maroon, the dark blue, and the dark red. This evidentiary way of supporting equity in recovery has been used in other places. It was used in Puerto Rico for two of its hurricanes. It was used in Florida, in Texas with Hurricane Harvey, and also in Louisiana for severe storms and flooding. What this has led to is the development of geospatial targeting of applicants for HUD recovery funding. And here, the action plans that are now being developed are based on mitigation needs assessments. And this is a way of distributing additional funds for mitigation programs. And what these mitigation needs assessments are requiring are basic risk profiles of the areas that have received a presidential disaster declaration. These risk profiles, like the map on the right, show the floodplain areas and areas that were flooded, overlaying with social vulnerability measures. They're interested in the unmet needs, that is, what money was spent already, what was the need, and what is the differential between those two. They want to know the critical lifelines that were potentially at risk, and they want some indicator of social vulnerability. But unfortunately, they don't tell you how to do it. And so the Social Vulnerability Index provides one mechanism for achieving that requirement on the mitigation needs assessment. The impact of this from an equity standpoint is if you don't measure it, it doesn't get managed. And so one way of thinking about the inequity and losses is, again, to return to the bivariate map and understand that those areas on this particular map that are the dark red, the policy options in these areas have to reflect not only mitigating risk, but also reducing vulnerability. Both of those need to be done in tandem. Those areas that are gray are those areas in this matrix that the patterns are largely reflective of the physical risk. And so the policy option in these gray areas should be measures that reduce the risk, reduce the loss. In the case of Florida, this would be housing elevation. In other places, it may be levees. It may be tornado shelters. It may be landscaping and creating space around your house for wildfires. The areas in orange are those areas that are dominated by moderate levels of loss, but the policy option there is to improve the social conditions, to reduce the vulnerability, because these are areas that are high in vulnerability. And reducing the vulnerability is a social transformation where you need more education, jobs, health insurance, and those sorts of goals. So what actions can we take? Well, I put them into 4 different buckets. We need to integrate our perspectives and information. We need to do this by going beyond a single sector, beyond a single hazard, beyond a single institution, agency, or discipline. In other words, we're really looking at a all hazards, all context approach. Secondly, we need to improve data and assessment. In order to enhance our collective resilience, we need to know where we are. We need to know where we're going, and we need to document it. Oftentimes, we don't have a baseline to know where we've started in this journey. So it's hard to quantify how we've progressed. We need to know appropriate outcomes. Are we talking about resilience to some ideal? Resilience to what? Or are we talking about resilience for a segment of our population? Resilience for whom? We need to maintain some data consistency so we can compare across places. And we need to align the local needs and data with existing local data collection so we're not overwhelming local efforts. The third one is we need to translate and share. And here we need to take the first two actions, what we might call informatics. And this must be translated into practice. But at the same time, the practice needs to inform policy and decision making. So we need to produce data that's usable, useful, and used. But at the same time, we need to collect data that's usable, useful, and used for those in practice. And finally, we need to reduce the inequities. And here we need to move from inequality to equity and justice, and we need to right the wrong. This means that we need to detect and monitor these inequities with empirical evidence, and we need to provide meaningful pathways for community-based engagement and collaborative decision-making. And this means you have to engage the community from the very start of any kind of research project or practical application so that everyone is on board and working toward the same goal. And with that, I will conclude. Thank you very much.
Thank you very much, Professor Cutter. So now our next speaker is Dr. Therese McAllister with the National Institute of Standards and Technology. The title of her presentation is Enabling Community Resilience Through Design Practices. Dr. McAllister, please.
Okay. Thank you, Jorge. And you can see my slides, I hope?
Yes.
Yes. And I just want to say that Professor Cutter's presentation provided a terrific introduction to what I'd like to talk about, enabling community resilience through design practice. So let me go to the next slide here. So I'm just going to give you an idea of the discussion points today. I want to talk about community resilience in the built environment, linking building design to community resilience and social impacts, which includes minimizing damage and losses, where damage is repairable within a specified time, and supporting the community. Buildings have a role in helping support recovery of social and economic functions. So these are kind of the base concepts trying to link building resilience and community resilience. So I'll cover design practice, some principles and available guidance for design, and a little bit on performance-based design, because resilience is not in our codes and standards yet, but there's a tremendous amount of work going on in that direction. And then the last section will focus on community modeling and assessments with NCORE. This is an environmental modeling platform that's being developed by our NIST-funded Center of Excellence for Community Resilience, and give you a brief example of one presentation that was shared with me on community development and looking at policies for future performance. So we'll start with resilience in general. This is based on the National Academy's report and some NIST and FEMA's definitions. Resilience is the ability to prepare for and adapt to changing conditions and to withstand and recover rapidly from disruptions. And as was noted in the previous presentation, this definition can be applied down to an individual all the way up to communities and regions. Our abilities to address each of these factors varies depending on whether it's an organization, the population, or the built environment, but we all have a role and we have to integrate these capacities to achieve resilience. So community resilience goes beyond mitigating risk and includes implementing measures to ensure that the community recovers its functions in a specified time frame. And just a key part of this is recognizing that the built environment exists to serve social functions such as healthcare, education, governance, business. Also, communities are actively addressing future hazards and ongoing stressors in their resilience planning. And here I'm referring to sea level rise, changes in rainfall intensity and frequency, flooding events, wildfire, the higher heat norms that are coming along. All of these may not come as discrete events, or they may contribute to discrete events and increase the damage and recovery demands that are ongoing. And this graphic is just trying to give you a pictorial summary of all these social functions that we enjoy from our communities, and indicates that what's needed to support those functions should dictate the functional requirements for our built environment. So I just want to start. First, let's think a little bit about the social dimensions. When you characterize the social dimensions at the community scale, you, of course, have to look at the population, their present and future needs, what the demographics are, vulnerable populations, employment sources, social capital. These all help where this refers to people's willingness to support each other, engage with each other. This has been found to be an important part of recovery. Social institutions, such as I mentioned on the previous slide, we need to understand what functions they're providing, if there's gaps in their capacity and their dependencies on other institutions. And then, of course, at the community scale, with a hazard event, you want to think about direct and indirect impacts. It's often the indirect impacts that cause extraordinary losses and damages. And they're not well measured. These statistics that we see are often based on insurance coverage or other things that are more easily measured directly after the event. But recovery data is a new area of focus, and I think we'll soon have much better measures of these indirect impacts. And this graphic on the right is just sharing a concept that social scientists have been aware of for a long time, but it's good for engineers to be aware of it as well. This is a figure adapted from Maslow's hierarchy of needs, and what it basically says is you have to have the bottom of the pyramid before you can move up. And after an event, we focus on survival. This is what emergency response is about. And then safety and security, where we feel safe to come back in a community and we can start to resume school or employment. And then we go on to some of these higher levels of social capital and growth and recognition, which is part of what we all like to do in our day-to-day lives. When we think about the built environment at the community scale, we of course have our buildings and our infrastructure systems, but we also should think about buildings in terms of what we term building clusters. And just like an infrastructure system is a network that provides a service, water or power, communication, transportation, throughout an area, building clusters do the same thing. So the example here on the right is for education. It's not a school, it's all the schools, the administration buildings, the bus depots, everything you need to make the schools functional. And of course, there's the dependencies on the infrastructure systems there that are noted. If there's roads that are down and the buses can't get the children to the schools and the staff can't come to the schools or the other areas of the educational cluster, then you aren't providing that function to the community. So it helps sometimes to think about that larger scale, not just the individual building. And then for resilience, we want to link these things. The built environment's performance will dictate what services and functions are available. And note here with social institutions, I am including economy and business. When there is damage and interruptions, then there can be significant social impacts from the individual level all the way to the community level. And depending upon the degree of damage and losses, you can end up with people permanently leaving a community, and this has long-term impacts. So a classic example, of course, is Hurricane Katrina. Many folks left and they did not come back. It has taken a long time for the New Orleans area to recover from Hurricane Katrina due to that loss of businesses and the population. So this is a pictorial of this concept, recovery of functionality. And I've got definitions on the right. Functionality is a measure of how well a building or lifeline / infrastructure system operates, delivers its required service, or meets its intended purpose. Whereas time to recovery of function is this discrete part after the event that measures how long it takes to restore the function or service, even with temporary measures, so that the community can continue recovering. And of course, what's noted here prior to the event is the condition is so important, whether you are in a community where improvements are being made, or maybe things are generally aging and not being repaired at a rate that's keeping up. That can dictate the amount of damage and loss and the time it takes to recover. And so in the Community Resilience Planning Guide, we use this as a way to help communities think about where their biggest gaps are in terms of their infrastructure and buildings. So an example here is for critical facilities, and you see the red boxes around buildings and wastewater systems, because these two have the largest gaps. So the green box indicates what the community says their goal is for 90% of their buildings in the critical facilities category to be operational or functional immediately after the event. Whereas with the wastewater system, they allowed 1 to 4 weeks. And you can see the blue boxes indicate what they think the performance would be if an event happened in the near future. And so this can help with prioritization of those scarce resources that communities have to understand how to better mitigate either damage to infrastructure systems or to buildings that will impact their ability to respond under critical facilities. So if we return to functionality for a minute, ASCE 7, our standard for minimum loads for buildings and other structures, addresses functionality in section 1.3 basic requirements. And it notes that structural systems should not prevent the function of the facility immediately following any of the design level hazard events specified in this standard. Now, this is limited to risk category 4 structures at present, and it lists things that might be considered, such as deflections, lateral drift, or other deformations. But this is kind of the stake in the sand starting this thought process. And there's a lot of work going on to how to better characterize this for design practice. So under codes and standards, we need to better define what functionality is both before and after events. And right now in performance-based design under performance objectives, there's work ongoing, especially for earthquake hazards, how to develop criteria to enable design of functional recovery. So some of this work that's ongoing came from a report that was requested by Congress to the National Earthquake Hazard Reduction Program. And this report was published in 2021. And they had 7 recommendations. And the 3 here in blue are being acted upon now by FEMA, NIST, and the USGS, as well as NSF. And the first goal is to develop a framework for post-event reoccupancy and functional recovery objectives. And to also consider how to address new buildings to meet functional recovery, and as well as lifeline infrastructure systems. And I'll just note here that even though this is very earthquake-centric, a lot of the thoughts and concepts in this document would apply to all hazards. So they talk about functional recovery performance levels for buildings. They talk about post-event reoccupancy, functional recovery, and then full recovery. So reoccupancy is the ability to occupy a building while it's being repaired. Functional recovery means that the building can be used for its intended purpose, at least in a large extent. So a business could resume even though repairs need to be made. And full recovery is talking about fully completing all repairs. And this is important because if you have another event, as was noted, so before the repairs are completed, you have a more vulnerable system. And the idea is that the more rapidly the repairs can be completed, the better the built environment will be able to withstand the next event. And on the right is for infrastructure systems. They use the terms operability and functionality. So they have 2 categories instead of 3. And this is just a graphic thinking about functional recovery for building types according to risk category. So we have critical infrastructure, critical buildings, risk category 4 is the red line there. Generally, it's expected that they will provide continuous function. They may have some level of damage, but fairly rapidly, they're going to meet their full functions. And you see the line increasing there because there's the thought that sometimes we want to improve the functionality of a system, not just return it to its previous state. And then similar lines are drawn here for risk category 3, which tends to be your commercial or institutional buildings with large gatherings, and then your risk category 2, which are most commercial and residential buildings. So these concepts, I think, are well understood, but the tools to actually determine whether they're being met or not is what's needed to be developed. And then more recently, there was a paper at the recent NCEE seminar at Salt Lake City, a conference, and it summarized target recovery times, both from design guidance and community resilience plans. And this may be, it's a lot of words, so I tried to summarize it briefly on the left. What the recovery goals are based on for buildings: probability of loss of function, peak drifts, limited damage, no residual deformation, or mechanical and electrical system functionality. On the community scale, it's time to reoccupancy, percent of buildings and lifelines that are recovered within a certain time frame, and maintaining the community population and businesses. So let's just talk about design practice a little bit here. We'll talk about some general principles and then go over the available guidance and then an example. So very happy to see some of the language I'm using being used by Susan Cutter. Context is so important. The key concepts for infrastructure resilience, where I'm including buildings as part of infrastructure here, are context, functionality, and dependencies. So you need to understand how your particular project supports community functions, what are appropriate performance goals and criteria, and if you're looking at an existing system, considering mitigation and recovery concepts together when comparing design alternatives. Functionality, of course, as we've said, needs to consider community social needs. And temporary measures are certainly part of that consideration, trying to get those functions back as soon as possible. And one thought, too, is sometimes function changes during recovery. Schools may be used as shelters, some examples like that. And then dependencies, as we all know, no system is an island. And this is a very common question. Many of you that work on building designs say, I can work on my building, but I can't ensure that all those other systems are available. And I think that's fine because your system, your building is ready when those systems are available. And it may be with some temporary measures, your owner or the occupants can resume their function. So it's thinking about these things and playing your role in helping the community get ready to recover from the event. So I've just listed here some resilience principles for projects, and this is based upon the 6 steps that we use when we talk to communities about community resilience planning. So, which is summarized in that graphic on the right. First thing is you want to identify your stakeholders, your owners, operators, end users, authorities and regulators. You want to identify the community project resilience goals and objectives, and maybe think about whether sustainability or climate adaptation requirements should be included as well. And then based on those goals, you set your project design and acceptance criteria, which should include functional recovery to the degree that's possible. And now you have the information you need to start thinking about alternative designs so you can assess structural safety, as it's always required, functional recovery, as well as consequences and dependencies. And just as we prioritize the gaps in recovery time in the previous slide, you can also prioritize alternative designs. Sometimes it's done through a benefit cost analysis, but we have to be careful not to make everything based upon economics. Sometimes there's other trade-offs that need to be made that need to be considered, and I've listed some examples here. So some design guidance that is available for buildings. There's FEMA P58 and Volume 6, Guidelines for Performance-Based Seismic Design of Buildings. And they cover performance objectives, utilities and backup systems, and expected performance of code-conforming buildings. And ATC 138-3, Methodology for Assessment of Functional Recovery Time. And here they address reoccupancy, building function, and recovery time. And for infrastructure systems, in general, there are not documents like we see for buildings. But Craig Davis, who many of you know, who previously worked for the LA Department of Water and Power, has written on performance-based seismic design for water systems. And this particular document that he published in 2019 looks at developing scenarios to assess the system performance, talks about identifying critical vulnerabilities and dependencies, and determines service losses and mitigation measures, modeling the restoration process to see if the target performance goals are met, and then expanding this method to other hazards. So I think this applies well to any infrastructure system, and it's a nice overview of the thought process. And then on performance-based design documents, so the topic listed at the left there, and then the particular document, you're all familiar with ASCE 41, which looks at existing buildings. Then the Tall Buildings Initiative also has some guidance that can be used relative to resilience if you think about your performance objectives going beyond simply mitigating risk. And then there's some other standards and pre-standards listed here for tsunami, fire, and wind. And soon we'll have one published on disproportionate collapse. So just looking at the performance-based wind design standard, it goes through, it was published in 2019, risk category, how one should assign risk category, thinking about resilience, community impacts through loss of service, and then it goes through identifying performance objectives and acceptance criteria. So I'm going to switch now to talking a little bit about the community modeling and assessment. As I mentioned, there's a NIST-funded Center for Risk-Based Community Resilience Planning. It's out of Colorado State University, but there's, I think it's about 14 universities associated with it. And one of the products is this interdependent networked community resilience modeling environment that integrates hazard impacts on the built environment, population, and economy. It can evaluate impacts of policy changes such as building codes, land use, and mitigation. And then I have a brief example just to give you an idea of some of the possibilities that NCORE can address. So just to better explain what this is, there's 4 areas covered: the physical infrastructure, economic health of a community, the social services within a community, and then there's quite a bit of work in terms of information science, all the data that has to be brought into the model, and then the results are also put out against metrics and in terms that hopefully will support decision makers. So we're working with 4 communities right now on helping them with their resilience planning using this tool. And this work has just begun and should continue over the next year to year and a half. So it will first look at damage and loss. And then it will look at interdisciplinary recovery with fully integrated supporting databases. And then it also allows the option to evaluate alternative actions to enhance community resilience and to inform planning. And the model always begins by modeling the community. So we've been using, there's a national buildings database that's managed by the Corps. It's been very helpful to rapidly bring in information about the buildings at the community scale. We also model either the transportation, electric power, or water networks. And then we have community economy models that look at the tax base, income, and impacts to different sectors. And of course, the community. which includes households and institutions. So I very kindly was given this presentation by some of our researchers in the center. This is from Oregon State University, Dylan Sanderson, Dan Cox, Rashad Amini, and Andre Barbosa. And this is looking at coupled urban change and natural hazard consequence model for community resilience planning. So they're focused on the Cascadia subduction zone in Seaside, Oregon. And you can see it's a reasonably small community, but it makes it a good test bed for looking at a lot of these concepts. So the idea was to look at how to evaluate resilience policies. And the recognition here is that if you change your building codes in a community, it takes time for those to take effect. And you can see that here between the status quo, continuing development within the community, and here's policy A with a different building code policy that may improve the performance of the community. And then they look at an event happening and what the damage and losses are, and then what the rate of recovery might be. So they started with identifying community resilience policies, which I'll go over in the next slide. And then they looked at how the community changes over time. They looked at population growth and land use and development. And then they looked at damage and losses from an earthquake event. So they had a number of planning scenarios. This first one was based on community planning. And here they had a cap on LOSR, here is low occupancy, seasonal rentals, relocating community assets, or else limiting any further high occupancy development. And then they had one on building codes, which they termed as low, moderate, and high. Now this is based off of HAZUS, where the low and moderate consider that if you have existing buildings, you limit their performance to 75% of the new building requirements. And so this is tied to what HAZUS has for existing buildings. And the high is assuming that it's a new construction and has to meet new code requirements. And then there was a combination of the two. And you can see they didn't use all of them, but they had a subset where the relocation, and this is west of a river, the Canicum River. And they also limited the building code changes to rentals and the low occupancy seasonal rentals. So what they found when they ran the analyses is that this cap on low occupancy seasonal rental had the biggest impact on visitors. It didn't really have much impact on those that remain in the community, the full-time residents. And the vertical axis here is the number of people exposed to a damage state greater than 1, which means greater than minor damage, that they can still remain in their homes, relative to the baseline, which was no further changes to the building codes. So when they stepped through these with the codes, you can see they had the better outcome for both the visitors and the full-time residents, looking at those 3 levels of codes. And then when they looked at their subset for those focused on rental properties, it did not have much effect on full-time residents, but it did have quite a positive effect on the visitors. And so this is just a very brief example of some of the things that can be done to help communities with their decision-making on how to improve their resilience over time. So I just want to close with a few thoughts here. Resilient buildings and infrastructure minimize damage, losses, and will reduce future expenditures. We all know communities really don't have a lot of resources, they're very limited, and resilience will reduce the demand on those limited resources. Buildings and infrastructure that limit damage to being repairable within a specified time is essential to supporting community recovery. And existing infrastructure is a significant portion of every community. Guidance is needed for both new and existing construction. We often start with the new construction because that is, an easier problem to address in many ways. In terms of guidance, there is resilience guidance for communities, buildings, and infrastructure systems. It is a starting point. It's not yet reached, design criteria, but there are efforts underway to focus on functional recovery. And there's a significant effort being undertaken by the NEHRP agencies for earthquakes. And with regards to climate, communities are addressing future climate challenges using available science and experts, but they are very much looking for national guidance or standards to help them because they're all making decisions at a local level. And ASCE and federal agencies are working on bridging the gap between climate science and its applications to communities and individual design projects. And Jorge, I will conclude there. Thank you.
Thank you very much, Dr. McAllister, for that great presentation. So according to our program, next speaker is Professor Benjamin Zaitchik with Johns Hopkins University. And the title of his presentation is Anticipating and Addressing Complex Climate Hazards. Professor Zaitchik.
Great. Thank you so much for the opportunity to participate. All of you can see my slides in the right viewing mode.
Yes.
Thanks so much. So it's a real honor to be able to participate today and talk with a community that I just don't get much opportunity to interact with. So I'm a climate scientist working on adaptation challenges, as are a number of our other speakers today. And what I wanted to do maybe is just lay out a few broad principles that are common in the climate world. Advance apologies if this is pedantic or old hat to some of you working on earthquake hazards. But hopefully some of this framing has a place as we all learn how to think more about the kinds of issues we just heard about in terms of equity and really creative thinking in our resilience strategies. If I were to summarize the main point here, which I think you're all aware of, is that it's complicated. And certainly that what we see in the climate world is that by embracing that complexity, engaging with communities that might not have been part of the original equation when you were thinking about the impacts of disaster, you can really both enhance resilience and hopefully avoid some blind spots and be really damaging. And so this opening image here is from New Orleans in the wake of Hurricane Ida. And I'll get to this in a little bit, but the main point here is that in the wake of Hurricane Ida, turned out there was a massive heat wave and a power outage. And so the biggest threat was heat. More people died from the heat in New Orleans than died from the storm. And so we had a situation in which being ready for perhaps a hazard that's different from the hazard you thought you were facing ends up being really critical. Okay. So I'm going to go through this, again, three general trends from my viewpoint that I think have been useful in climate hazard analysis. Talk first about a risk-based framing. Again, it'd be interesting to see how this is similar or different from the way things are viewed in the earthquake world. And then talk about these problems of compounding cascading hazards like Ida. And talk finally about propagating shocks in time and space. So I'm going to start with this diagram, which, it's in the world of flowcharts, it's one of those schematics that maybe causes some headaches the first time you look at it. And this is from the Intergovernmental Panel on Climate Change, the IPCC. And this is a risk-based framing that has really prevailed in climate science for some time, and certainly since the IPCC reports from early last decade. It first appeared in 2012 IPCC reports and has grown since then. And the basic idea here is that risk is the key concern, and that risk exists at the intersection of hazards, exposure, and vulnerability. Again, terms we've already heard about a lot this morning. In the climate change context, we're very worried about how risk leads to impacts and how these impacts, in turn, end up feeding back on two things. Could be feeding back on the climate, which again might be less relevant for earthquakes, but in our situation, experienced risks that lead to impacts that might impact your energy systems or your location of people will influence things like natural variability of climate as influenced by anthropogenic climate change. But also, and this I think is in common between climate and earthquakes, you're going to see impacts that feed back on your socioeconomic processes. Now, some of the terms here don't make sense in the earthquake world, but if we simplify just a little bit, I think that we can see that this diagram still works, even if you take something like, the socioeconomic pathways associated with greenhouse gas emissions or anthropogenic change influencing the intensity or frequency of the hazard. We can take those out of here, and we still have a risk-based framework that's relevant, I think, to any kind of hazard, and that is still really the heart of what we're looking at often in climate, because climate change is a trend in risks, right? It's a stressor. And very often in the climate world, we're thinking about occurrences that might be altered from the historic record, but are not entirely novel, so similar to an earthquake situation. I'm just going to take a minute on terminology here. I think, based on what we already heard this morning, folks are familiar with these terms, but I might use them slightly differently. So here, in this diagram, impact is effects on both natural and human systems. And so sometimes that's called by other names, but it's not just, loss of life or something, or loss of property. Risk, meanwhile, is a fairly standard definition of risk that we use in the climate world, with perhaps the tweak that we're often thinking about trends. And so when you look at climate analysis of risk, you just want to distinguish between whether they're talking about total risk or a trend in a risk. Because sometimes when we talk about the risk of climate change, it's that trend as opposed to the baseline risk. But same concept in general. And then the hazard in this case, again, in the climate world, we're constantly contending with both natural and human influenced events, right? And so that distinction matters a lot to us when we think about attribution and when we think about assessing trends for future risk. But it can be a fully natural climate hazard. And in that sense, it could be similar to an earthquake hazard that humans had nothing to do with causing. Exposure. And so this is, again, probably be pretty simple in our similar in our communities, where we're talking about the presence of these people, ecosystems, resources in harm's way. And then vulnerability being, again, this propensity or predisposition to be adversely affected. And that can be because of, your personal characteristics. It can be because of societal dynamics. It can be because of your infrastructure, right, in a way that kind of crosses between exposure and vulnerability. Vulnerability being when there might be some systematic predisposition associated with that exposure. But all of these are of interest to us as we think about risk. Now, this diagram, the middle of this diagram here, in the climate world, we call this the risk propeller, okay? Because it kind of looks like a propeller, right? And so one point that I think has been an important trend recently in our understanding of climate hazard has been to add a blade to the propeller. And so this is an important paper that first appeared last year in 2021. I think there was some coordination between this and the IPCC reports that came out early this year in 2022, because these diagrams also feature in the most recent IPCC report on adaptation. And what you'll see here is the propeller has sprouted another blade, and that blade is the response blade. And this addition was a recognition of potential for things like maladaptation, for inequitable response to disasters, for all of these factors, again, that we've heard about today a little bit already. And so what this modification the propeller does is it encourages us, kind of forces us to really be thinking about how a response to a hazard either does or does not enhance resilience, reduce risk, or perhaps accidentally increase risk, both for the ongoing disaster and for any future hazard. Another modification that was made to the propeller in this same paper was the recognition that the blaze of the propeller might push one towards oversimplified thinking. Not necessarily, but they thought that maybe making this a little more explicit would be important. And what the point made here in this schematic is that if you're talking about a hazard, you aren't necessarily talking about just one hazard. You could be talking about interacting hazards that can be aggregate, they can be additive in terms of their impact on risk. They could also be influencing each other. And of course, influencing across the blades as you look at the hazards, exposure, vulnerability, and response. And so really thinking about the directionality and interactionality of these influences on risk has been a big theme in the last few years, at least from my viewpoint, in the climate risk literature. So here's an example of a fairly mature application of this propeller. And this was to an application to a recent European heat wave. And so if you start on the top left and look at the hazard, and this was from 2018, in fact, it applies even more so to the current year, the current summer in Europe. And what you see there is that the heat wave was perhaps the clearest climatological signal this summer, in 2018, as well as the summer. But then it ends up interacting with other hazards. And so extreme heat and wildfires interact, right? Heat increases the probability of wildfires. Wildfires then can have local feedbacks on the experienced heat in areas affected by those fires. Meanwhile, you had heat in two different regions that was causing an additive hazard when you thought about its impacts on infrastructure, for example, river infrastructure, like we're seeing this summer. If rivers are low because of heat in different places, that's an additive hazard. And so on. You see the interaction with drought and winds. If you look at some of the other blades of the propeller, when you think about the response, focus on that for a moment, you can see that in response to these climate hazards, the heat, but also the fires and the drought, you end up with certain restrictions, restrictions on water use, restrictions on where you can go. And then when you combine that with, maybe they didn't realize this until now, but shortcomings in planning and weaknesses in the firefighting response, you can get additive hazards. And again, interacting then where evacuations affecting your firefighting and some other, the early spring soil moisture depletion, because that's influenced by agriculture and human land use, that would then be viewed as an interacting effect where it ends up influencing your firefighting capabilities. So could talk about this diagram probably for the remainder of the time. But as you see, the idea here is really to recognize, to acknowledge, and then hopefully address these interactions. Now, this is a fairly mature view, right? And probably heat waves interacting with droughts to influence wildfire risk is one of the clearest cases of physical interactions. And risk to infrastructure is a place where some of the impacts are pretty well defined. It comes as a surprise to nobody that a climate extreme will be posing risks to infrastructure. One area that's interesting that I've been able to get involved with just very recently is with some communities that are now moving to understand how climate is a risk to them. And again, this is something that's an obvious trend because of social and physical trends in climate, that this recognition is growing now. And I don't know how that maps onto earthquakes, but again, I think with our increased awareness of things like inequity, environmental justice issues, the need for responses that account for all people, hopefully there's also an increasing recognition in adjacent fields to earthquake engineering, thinking about how you might apply such a paradigm. So in my case, here's a slide that I stole from a talk that I'm giving next week, which came as a surprise invitation to me, which was the American Rhinologic Society. I think I just said that. So these are the nose doctors, right? And they are worried about all kinds of things having to do with rhinosinusitis. And so there's this new recognition that climate is influencing this, that doctors are seeing, for example, allergy patients show up with severe seasonal allergies that are no longer seasonal, that are coming at different times, or they're experiencing them in places that had not experienced a particular kind of pollen before. But even some of the non-allergenic diseases, they're worried about things like how things like humidity, for example, might be affecting some people. And so this is a less mature version of the propeller that we're just starting to work on. We're saying, okay, we just got a list of things here, and we need to figure out how they're interacting, figure out what really matters, and how the health system might want to respond. And so just showing this as an honest view of what this looks like when you start doing it, right? It's still worth starting, I think, because eventually you can try to identify the connections that are most important. Okay, next I want to talk about compound and cascading climate hazards. And so this is a photo from earlier this year in Kentucky. And so this was a case where I'm sure everyone here is aware of those devastating floods in Kentucky. And much like Ida in New Orleans, the floods in Kentucky were followed by an extreme heat wave. And so here's someone trying to do some rebuilding in a situation where there's little infrastructure that's functioning, power is out, and it's extremely hot. And so putting this at a finer point on this can be important. We should, again, try to map out how these different hazards interact. So, left and middle here, we're just seeing what I showed before, right? Your four blade propeller for risk, acknowledge the interaction that happens across them, and then thinking about how different risks interact. So this interaction of hazards, vulnerability, exposure, response to influence a risk, but these different risks can interact as well. Or you might have aggregate risks to infrastructure and health, for example, associated with independent disasters, right? That aren't actually functionally linked. You can also have these unidirectional or bidirectional interactions between different kinds of risk, and you can have cascading risks, okay, where one leads to another in this really clear way. And so just a couple examples of that from recent years and how this paradigm has been applied. So coming back to Ida for a second, because I think Ida was such an interesting one for multiple reasons. So Ida, and just talking about New Orleans, Ida was also interesting what it did in New Jersey, right? But Ida in New Orleans, again, we're seeing here this response to the heat that came right after it, and that was the leading cause of death. And so at first you might think of this as an aggregate, right? Like there's a risk of heat stroke associated with a heat wave. There's a risk of, drowning or other injury because of a hurricane. They happen to come one after the other, right? And that's true, right? We can usefully think about some of the risks this way. But another thing that's happening is that there were really three risks going on at this time, at least three major risks, because you had the heat wave on top of the hurricane, and you had COVID. Okay, and COVID ends up being a big consideration in this because your response to one risk might influence the other risk. So COVID was there in the background. The hurricane comes through. How do you deal with evacuations when you've got a respiratory illness around? Okay, so that was a big issue. That's been an issue in hurricanes from 2020 and 2021, as well as this coming year. But you also have a response to heat problem, right? Like what's the one thing that people try to do when it's hot? Get to a cool space. What if power's out? Well, maybe get to a centralized place with a generator that's keeping things cool. Do you want people crowding into cooling shelters when COVID's around? These kinds of interactions end up being an area of focus where we're seeing hazards that are essentially independent. The hurricane didn't cause COVID, right? COVID didn't cause the hurricane. But as these disasters play out with their own independent risks, those risks end up being sometimes altered in character or amplified by others that then might change your response, right? Maybe you need to respond to the hurricane or the heat differently because there's this other threat. Another example, again, in this world of heat, drought, and wildfire. So 2021, could do, I'll do this all for 2022. It's been another heck of a summer. But in 2021, we had that really record-setting heat, and there were two events back to back. The southwestern United States had terrible heat in late June, being on to early July, and in the northwest had what got even more news. Right? So unusual and so record-shattering what happened in places like Portland, Seattle, Vancouver a couple weeks later. And so there's questions like, okay, do the heat, drought, and fires cascade, right? Are we really seeing a situation where maybe the drought leads to the heat or the heat leads to the drought, which then leads to the fires? And so this is worth understanding because I think waving hands, it's easy enough to understand this, right? Like that makes sense that these would interact. There's a pretty clear functional link between how dry things are, how hot things are, and how much things burn, right? That we all get that. But on an event-to-event case, you want to put people like me who are climate scientists, you want to really understand that and quantify it. both to understand how the system's working, because it's a very complex system, but also to think about response and preparation for future risks. And so in this case, we did a study, and I'm not going to make you sit through my talk on my own climate paper, but this was work done by Mahmoud Osman, a postdoctoral scientist in my group, where we ran some models and said, okay, was it hotter because it was dry? So if we didn't have the drought going on, would the heat wave have been less severe? And we're looking at the southwest here. We're not looking at the northwest. We're looking at that first part of the heat wave. And just to make a point here, red here indicates places where it was at least a couple degrees on average, and there's 2 degrees Celsius warmer on average for 2 weeks. So it's a pretty significant difference. And it was hotter with the drought than it was in simulations without the drought. And so you can see there's some mixed signals in some places in the desert where it didn't matter at all. Where you get into like the forested ridges going up through some of Arizona and Utah, or some areas over here in California, there's some pretty significant feedbacks going on where we say, yes, the drought did cascade into what ended up being this record-shattering heat event. And indeed, the heat event, it turns out, also fed back onto the drought by increasing evaporative demand and making the drought worse. So we have a compound bidirectional hazard, which then eventually we address fire ourselves in this study, but we can start to see how these physical interactions are really playing out. Okay, so climate has a lot of these coupled systems involved. Earthquakes, I'm sure that you guys have different considerations. I myself am ignorant of any potential feedbacks onto earthquake risk in terms of the hazard itself. But as earthquakes interact with other, earthquake vulnerabilities, might be the product of earthquakes and other hazards, you might start to see some of these interactions. Last example I'm going to give of a cascading disaster, and it will lead into my last point, is cases of cholera. So cholera, we spend a lot of time working on cholera in my research group. Climate-sensitive disease for obvious reasons. It's waterborne, right? And the one of the interesting things about cholera risk is that you find that sometimes you get increases in cholera risk during drought. And why does that happen? And we had this example in 2017 where this was happening in East Africa. And that happens for a couple of reasons. First of all, people might lose access to their preferred water point, and so they're drinking from compromised water sources. You may also get concentration of contaminants in shrinking water bodies. And also people maybe have to relocate. Maybe they end up in a refugee camp in a case like a famine, and that can lead you to be living in unsanitary conditions. But cholera also ends up happening. This was 2 years later, 2019, and just in southern Africa. And this was where we had a cholera outbreak in response to Cyclone Idai, which was a big storm that hit southern Africa and led to massive flooding. And so flooding can also lead to cholera. Why is that? Because it leads to, there are a couple of hypotheses. One is at least a contact with contaminated waters. Things flood in and put you in contact with them. Another possibility is that you get spillover of some contamination pools. And also, again, relocation as people have to flee regions, putting themselves into vulnerable positions. And so I mentioned this because I think to me anyway, it highlights the complexity and kind of coupled natural human element of cascading risks, right? Where you need to worry about people moving, you need to worry about how a hazard in one place might affect another hazard somewhere else. Okay. And so again, I would think there are connections between climate and the earthquake world here, in that if you have an earthquake that really affects a community, are there other communities that might be being affected as well? See where I turn this camera on, so I should probably finish up. The final thing I'll put here is just on these propagating shocks, and I won't. I'll cut short a little bit on talking about this. This is an image of the vegetation anomaly right before the Syrian civil war. As a lot of you are probably aware, there's always been this discussion of how much this massive drought, the Brown and Gates drought, might have played a role in the destabilization of Syria. So we don't have time to get into that. But the point here is that the location of the drought and the location of the unrest were different. And we studied this in Ethiopia, showing here a kind of our view of Ethiopia when looking at like food security impacts of a climate shock. And there are two things on this map that matter. One are the colors. These are different agroecological zones. So those would be the places that determine the vulnerability of food production by agroecological zone. And then you have these yellow dots and polygons around them. Those are market centers. So that's going to influence the propagation of the shock. And to understand this, what we realize is it's not sufficient to simply look at crop production. It's not sufficient to simply look at the climate hazards' direct impacts on food production. We have to look at the whole food system. We do this through a multiplayer microeconomic model, which required that I move out of my comfort space and really work with some systems modelers to understand how different players, livestock producers, storage operators, consumers, are all interacting in this food system across different market sheds. And so what happens then is, well, if we have a major drought with a crop failure, which somewhat resembles the 2015 El Nino drought that massively affected Ethiopia, what ends up happening? And what we see is that if we impose this drought down here in an area called Oromia, you see the drought happened here around month 30 in the simulation, a loss in caloric intake for men and women in Oromia, but you also see a reduction in caloric intake in the capital city of Addis Ababa because markets link the two. Okay, so you see the hazards in both places. Question then is, what do you do about it? And you can think about different interventions. You can put these into the model and say, well, what happens if we take any of these favored interventions in case of a food security crisis? And say, well, what happens to food security, at least in our simulation of these potential responses? And what you end up seeing is that if you under no intervention, there's about a 2% reduction in caloric intake. This is in Oromia specifically. Subsidies didn't do much to help that. Direct aid did because it got to the most vulnerable. Transportation expansion, which is the idea that, we can make it easier to get in and out of a region, was a maladaptation in this analysis, because what it basically meant was that those who successfully produced their crops were able to export to get higher prices in the capital city, leaving Oromia. And so depending on your scale of analysis, that might help with hunger somewhere, but locally you actually exacerbate hunger through this kind of intervention in the absence of complementary policies. Again, I'm running out of time here, so I'll leave it at that. But the point being here that by accounting for the network effects, you can maybe come up with a different conclusion about what the most effective intervention is. And again, this would be just a view of where that response blade and the interactions particularly become really important. All right, I'll finish up there. Again, just hopefully maybe some of these concepts weren't, I don't know how much they're new for this community, but the idea of risk-based framing, thinking about these compound and cascading hazards, and also how you have propagation of something like a natural hazard shock, we're finding to be pretty important. Thinking about climate resilience, and maybe there's some opportunity for cross-fertilization across communities. All right, thanks so much.
Thank you very much, Professor Zaitchik with Johns Hopkins University. So now is the time for discussion panel. So we have 30 minutes for attendees to address questions or make comments to our three panelists in this session today. So please use the Q&A option below on your screen if you want to make any questions. So I have a question or comment to Professor Susan Cutter. I am a geotechnical engineer, so what I'm going to do is just to think aloud about something that is not my field. I would like to share with you and to receive your comments. So I think that, at least for me, the current pandemic has unveiled this more clearly, the importance of social vulnerability to natural hazards, including earthquake hazards. I think that it was very, very clear and very pathetic to see the relation, for example, that in the pandemic, who were the most affected. And also at the same time, I think that we are talking about environment destruction, that there are forces, economic forces, destroying, without any consideration of the environment. We see that the influence, the climate change is generated also maybe by the same forces, economic forces, whatever. This is inducing problems in the social vulnerability, poverty. After during this pandemic, I've seen different news here there that the rich people became richer and the poor people became poorer. So not everybody was affected. So, and also that we are living in a world in which they say, that 1% of the population enjoys the 99% of the wealth. So it seems to be that the roots of this problem of social vulnerability, if we want to address it just only from an engineering point of view or technical point of view, probably will be very limited. So I as an engineer, I would like to see a horizon that where we are going to heading and how to deal with that. I don't know if you understand, Professor Carter, but as I said, I'm just
no. I understand. I think one of the first things to think about is reframing our hierarchy so that we put people first and not buildings and structures first. So we think about the people who are living in these environments. We think more locally about what can be done to eliminate or reduce the structural barriers to poverty, to inequality, to the inability of people to get health insurance or childcare, which limits their social advancement. The issue is it's very complex, and it can't be done by a single discipline or within a single sector. So if we wanted to tackle this collectively, my sense is the way to start is to collectively focus on a particular place and start there and see what can be done to resolve some of the social issues and concerns and barriers in particular places, along with reducing disaster risk at the same time. I think we're moving in a positive direction at the moment, where resilience is at the federal level. It is part of the mantra, and now we see all of the federal agencies are now interested in inequality and inequity, and are mandating that there be considerations in all of their programs. So I think there's an attempt, at least at the federal level at present, to begin to redress some of those disparities that we've seen over the years. So I'm really hopeful that we're going to get there. It's just going to take a while to do it. And Jorge, I thought you were absolutely astute in observing that this really came to the fore during the COVID crisis. And that really showed where those disparities are in terms of the social structure of this country in particular.
Yeah, and it seems to be that again, with the monkeypox, we are seeing the same thing.
Yeah.
So nothing different.
Yeah.
Nothing different, unfortunately. Okay, thank you very much, Professor Carter. There is a question here, and I guess it's for Professor Benjamin Zaitchik. The propeller from Heidi Steiner, the propeller diagrams were really interesting. Do you use these to communicate with communities or researchers? Do you think communities would find them helpful in understanding interactions?
Yeah, I think that's a really interesting question. I have not a diagram with most of the communities we work with. I think they are probably better for kind of research and analysis purposes than for, when I think about communities, some of the direct community outreach we do on climate vulnerability. But of course, communities is a broad term. So by communities, we also include communities of, urban planners or health agencies, that we work with at the city level. I think absolutely the diagrams can be useful there. So I think they're useful when working with practitioner communities, and we've done a little bit of that. Not yet directly influencing operations, but at least in terms of thinking about new areas to work together on. I am less confident that they're the right entry point when you're talking about a broad public interaction, but I haven't tried, so I could be wrong.
All right. Thank you very much. So, Professor Adam Rose, I think that you want to say something. I'm going to unmute you.
Okay. Hi, everybody. This is Adam Rose. Can you hear me?
Yes.
Okay. I'm at the Saul Price School of Public Policy at USC and also Director Emeritus of the Center for Risk and Economic Analysis of Threats and Emergencies. So my question is to Susan. We have good metrics applied to equity issues such as the Gini coefficient, the Atkinson index. What do you think are the best measures or metrics that are comparable for environmental justice, or are there any at all yet?
Great question, as usual. The environmental justice metrics are not quite at the same level as things like the Gini index at the moment. It's a work in progress. There are multiple agencies that are trying to develop more robust indicators for these. There's efforts underway, I believe, at EPA in particular, but also at NOAA, trying to pull information together in a systematic way. But it's really difficult. I think they're having a slow go at it because of just the variability in how they're defining and using the terms and the data that are necessary to put into such modeling.
Okay. Well, thanks for telling us about those things. I may write to you directly and ask for some links. The one issue when you talk about an index composed of several indicators is the weighting problem. What weight you assign things, and over and over again you see people just give everything equal weight. And I hope we can improve on that, not only in this dimension, but other dimensions talked about today as well. I think that's one of the pieces of unfinished business in many types of indicators.
And I think the weighting issue is perhaps one of the stumbling blocks because it gets into the value judgments of justice for whom and justice to what.
Right. Well, I'm lucky to be an economist in that we have it easy with weights. Everything's in dollars, so it weighs itself. So,
right.
But it's tougher for others. So thanks a lot, Susan. Thank you, everybody. I enjoyed the presentations today.
Thank you.
Terry, bye. Okay.
Thank you very much, Professor Ross. And here we have another question, and I guess it's from Dr. McAllister. What are the examples of seismic retrofit of critical infrastructure can also help address climate change and social justice?
Okay, so that's, I guess, a two-part question. Let me address the climate change piece first and then the social justice. So, for instance, when you are thinking about climate change, I think it's generally accepted there's no direct impact on earthquake events at this time that we're aware of, but it does affect rainfall, sea level rise, some of these other events that can have an impact on building design, either through, say, landslides that occur later or ground saturation that might affect your performance of your building. But think about, for instance, that you have a flood event, even though your primary hazard is earthquake, and you have all of your mechanical, electrical equipment located at the lower level or in a basement level, depending on where you are. Now your entire building is non-functional until you can get those things repaired. So if you want to move those up to a higher elevation, that then changes your mass distribution in your building, and you have to start accounting for that. COVID brought up the issue that maybe you need larger air handling units, for instance. So as we're addressing these new challenges, it can affect building design, either from the structural perspective, which I think many of us here are focused on, or else from the entire building performance. It is certainly worth thinking about what these other hazards can do to the building that's been designed around seismic events. Now, in terms of social justice, I typically think more about existing infrastructure systems. And that is because many times when we look at these disaster events, it points out to us very clearly that buildings and infrastructure systems in areas where people at the lower rungs of the economic ladder perform more poorly, or they don't have the resources to wait it out. They don't have the money to go stay in a hotel or to move out of the area and come back. And so in some ways, they need greater capabilities than those that do have those resources if the community wants to keep them there as community members and make sure that this issue of equity is being addressed, that they're all valued as community members.
Okay. Thank you very much for that response. So any other questions or comments for our speakers this morning? So a few years ago, several years ago, actually, we did a study, seismic vulnerability of school buildings in town, which is close to the border with Mexico. I mean, it's on the Mexican side. This area is a semi-desertic area. Of course, the earthquake vulnerability of those school buildings were very, very high. But also at the same time, we observed something. We observed that because this is semi-desertic area, the temperature were very, very high during the summer. And when we were trying to evaluate and provide recommendations about response, etc., of course, we had to say, okay, what happens in an earthquake, of course, during the summer, and what's happening if an earthquake occurs during the winter. And during the summer, of course, we have to consider that, probably the air conditioning in those buildings that where this system were available will be disrupted, and also the water supply system will be disrupted. So, and obviously, even though from a building point of view, the seismic vulnerability were the same, because of the disruption to the air conditioning, the water, etc., the heat problem will take place there. Will magnify more the problem. In your presentations, then it reminded me that problem that in those years we realized that an earthquake can exacerbate something or create something new. Not that the people will not kill from the earthquake itself, but will be killed by the heat. And this is something that you were pointing out also. So can you provide more comments about this in terms especially of social approach or how to deal with this?
There's the unmute button. All right. Yeah. Well, thank you for bringing that back up, Jorge, because it's really something I think that we're all collectively struggling with, right? Anyone who's working in these complex systems, and I think that in some cases, I think that a small variant of the standard approach works, or maybe it's already incorporated in the standard approach. So, I mean, in your example and my example, or one of my primary examples, we're talking about an infrastructure failure, right? And so when infrastructure fails in response to something like whether it's an earthquake or a hurricane, right? Then the ability to then anticipate that, well, that will then change vulnerability to something else that wasn't necessarily a hazard otherwise, right? Heat is in general a hazard to people, but maybe to most of the population, it's an easily avoidable hazard because you're not particularly compromised and because you have access to cooling, right? It only becomes a more widespread hazard that requires the scale of intervention when the infrastructure fails. And so I think just thinking through the implications of failed infrastructure, which is something that I know that emergency managers already do to quite an extent, but keeping that front of the mind can be really important. I think when it comes to some of the surprises, that's where surprise like things like what happened in Paris this summer, where people were having smoke inhalation hazard, right? And so why is that happening in Paris? Because there are forest fires outside of Paris that were unprecedented because of the heat and the drought, right? And so they have a situation where a health system, not just a health system, I mean, the emergency responsibility in general, but also the health system needs to be ready for the kinds of hazards they are not used to facing, right? And so to be ready for those kinds of things, sometimes it comes through, I talked about how we try to embody this in a model, kind of a research study. But often I think the most useful things are these tabletop exercises, right? Thinking through the potential cascading and unexpected hazards with the right group of stakeholders. So we're trying to do some of that work, hasn't yet been approved, but when thinking about things like coastal hazards affecting communities under a climate change trend, right? Or places that were not previously vulnerable to something like flood-induced mold contamination, any of these things that kind of come after a hazard and now is affecting communities that weren't used to having that happen before. That's where you need to engage communities that might be surprised to hear from you, right? Or surprised to hear from their counterparts because they didn't view themselves as part of the equation for these hazards. And I think really broad convening for these kind of targeted serious gaming exercises and things like this, I found to be pretty useful. I'm sure others in this call have done similar things and have other experience, but I found that can be a pretty useful way to get people to recognize themselves and their expertise as part of the solution.
Yeah. All right. Thank you very much. So any other questions or comments?
Jorge, I'd just like to offer that even though this is a tremendous challenge, this is an opportunity for engineers as well to become more thoughtful and informed about these potential disruptions in the function of the building or its intended use, and being part of that larger team, right? The design planning team for the building to bring this up or to identify things that can be done to address these hazards. So it's a value added opportunity. And I think it's really important for structural engineers and geotechnical engineers to start thinking about this as they're going forward in practice. And, communities are doing it today and they're making decisions based on what's available. And it's highly variable between communities depending on who they bring to the table and what data they use. And I'm very aware, right, of engineers' liability and practice and things that have to be addressed. But still, we all need to start being more educated about these issues that we've talked about today so that it's part of our thinking and planning as we go forward. And I just really would like to make that point so it doesn't always remain what everybody else is doing on a broader scale, but it doesn't affect engineering practice.
Yeah, that's very, very true. And I think that actually, one of the reasons that we organized this colloquium today was because we want to raise more awareness. And I realized that even including myself, we don't understand exactly all the extent of climate change could impact our practice, our daily practice, our design procedures, etc. We have some kind of idea, but we don't see yet the connection, unfortunately. And I think there is a connection. And also something that is resonating still in me and will resonate maybe for the next week, even though engineers are in charge of buildings and infrastructure, Professor Carter is put people first. So that means that this, of course, this should be a multidisciplinary work. Because for us in engineers, at least I don't want to speak for all engineers, at least for me, based on my more than 30 years of experience. As engineers, I don't feel trained to interact well with people. I think that there are other professionals trained for doing that. And we have to maybe team with them, work together to address the needs people, and then how we as engineers can support those efforts. Because actually, at least personally for me, the pandemic was very pathetic to see all these social issues behind. And then realizing that it's not only about the pandemic, it's also about other natural hazards. So, yeah.
I think an important thing to think about is to question the assumptions that you have. You made the remark about losing the air conditioning in an earthquake and in the Mexican community that you were talking about. The first thing that popped into my mind was, why did you assume that everyone had air conditioning?
Yeah, that's true.
Right?
That's true.
So just the kind of the basic assumptions that we make. Who's using this building? How are they using the building? Are there restrictions to their use of the building, perhaps in terms of their age, their infirmary, all kinds of things that you can just begin to question the assumptions that you're making going in when you're thinking about that design and purpose, and the idea behind the functionality.
Yeah. There is another question here from Juan Connelly with the California Seismic Safety Commission. How do engineers educate ourselves or to add to our toolboxes to work more efficiently with public health professionals to address climate hazards? So I think maybe this is for the three speakers, if you have something to say.
I don't know that I have the answer, Jorge, but I will say that at least at the federal level, our engineers here and social scientists at NIST are working with some other federal agencies that are looking at public health and trying to think about resilience in terms of the public health aspect, social issues, and the role that it's mostly housing plays in it, but it's also the built environment. And so there is some thinking going along those lines, but it's certainly an area I think that could be further developed. Certainly public health is one of those social functions that's closely tied to the quality of the built environment. Just look at what's happening in Jackson, Mississippi. I mean, if we had no potable water in our communities, right, it is a disaster. It is a total disaster. They have serious health issues down there, and it is very closely tied to infrastructure. So it's an important topic, but I don't I can't really fully answer the question.
And it's the inequality in the infrastructure. I mean, if you read the news reports, that aging infrastructure is very much a structural inequality consideration. Yeah.
Yeah, and the other thing I think is a great question, and it's something that we're actively struggling with. Those are state universities. So, where I sit at Johns Hopkins University, just a few years ago, we launched a new department on environmental health and engineering. Kind of poses exactly this question, right? How do you make sure that people are really trained in the engineering know-how, are also thinking about the kinds of justice questions and impact questions that Susan has raised today. And so, that's a degree program way of getting there. But I think the more people that ask these questions, the more we're going to be able to form the communities, the programs, the networks that we need to have ourselves in the right position.
All right. Okay. Thank you very much. Any other questions or comments? Okay, so if there is not any other question or comment, I would like to thank our three distinguished speakers today, Professor Susan Carter, Dr. Therese McAllister, and Professor Benjamin Zaitchik for these great presentations. They were very enlightening and very informative for all of us. Thank you very much. And we are going to have a 15-minute break. And then we are going to resume with the following session number 2 at 10:30 Pacific time.